Watch what happens when we apply two different transformations to these vectors. One glides smoothly to its new coordinates. The other stretches violently, accelerating off the edge of the frame toward infinity. To understand why that tearing happens, we need to define our environment. We are working inside a normed space, a vector space equipped with a strict mathematical definition of length, called a norm. When that space is complete, meaning every Cauchy sequence converges to a limit within the space itself, we call it a Banach space. This is the primary stage for functional analysis. Inside these spaces, we use linear operators to map inputs to outputs. A mapping is linear if it perfectly preserves two operations, vector addition and scalar multiplication. In finite-dimensional linear algebra, the algebraic property of linearity is sufficient. It guarantees that any transformation will behave predictably across the entire space. But infinite-dimensional spaces lack that structural safety net. Linearity alone cannot prevent a space from tearing. To maintain stability, we have to introduce a completely independent constraint, boundedness. A bounded operator is defined by its geometric limits. If we take a unit ball in space X and apply the operator, it transforms into a new shape in space Y. The operator is bounded if we can draw a rigid sphere of radius c that completely encloses that new output. This is distinct from the bounded functions found in calculus, where the range itself is limited. Here, as we increase the size of our input ball, the output ellipsoid scales proportionally. The outputs can grow infinitely large, but only at a restricted rate. Boundedness describes a capped ratio. The length of the output vector can never exceed a specific multiple of the length of the input. Def 2.71 of the Kreyszig text formalizes this. An operator t is bounded if there is a real number c such that for all vectors bex, the norm of tx is less than or equal to c times the norm of x. If we divide both sides by the norm of x, we isolate that constant c. It represents the absolute maximum multiplier the operator is allowed to apply to any vector's length. A bounded linear operator acts as a universal speed limit on geometric stretching, preventing the catastrophic topological distortion possible in infinite dimensions. This diagram shows a vector sweeping along the surface of a unit sphere in space X. We can track its corresponding output tracing the perimeter of the ellipsoid in space Y. To find the smallest possible bounding constant, we let the sweep continue until we hit the exact vector that yields the longest possible output. Right here, we label the length of this maximum vector as the norm of t. This maximum stretch factor is the operator norm, represented by the notation t enclosed in double vertical bars. It is defined as the supremum, the least upper bound, of the ratio of the output norm to the input norm for all non-zero vectors. Because the operator is linear, we can simplify this calculation by looking only at the unit sphere. The operator norm is equal to the supremum of the norm of tx when the input length is exactly 1. Quantifying this stretch factor allows us to treat entire transformations as individual points. We can now measure the size of an operator and place it inside a brand new vector space of its own. We can verify this on familiar baselines. The identity operator maps vectors to themselves, giving it a norm of exactly 1. The zero operator collapses all vectors to the origin, resulting in a norm of 0. Theorem 2.7-8 establishes that in any finite-dimensional space, every linear operator is guaranteed to be bounded. In infinite dimensions, specific operations act as structural stabilizers. Watch as this chaotic wave function passes through an integration block, exiting the other side as a smooth, low-amplitude curve. Integration calculates area. It inherently averages out and suppresses oscillations, meaning the output cannot stretch infinitely relative to the input. It is a naturally bounded operator. The right shift operator on sequence spaces is another bounded example. Because the right shift merely moves terms without altering their values, it preserves length perfectly. This results in a norm of exactly 1. Matrices, integrals, and shifts represent the structurally stable side of functional analysis, where the operator norm safely limits geometric chaos. This coordinate plane tracks the interval from 0 to 1. We have plotted several polynomial curves, t squared, t cubed, t to the fourth. We measure them by their highest peak on this interval. Since the maximum value of t to the power of n on this interval is always 1, The norm of every input function is strictly 1. Now we apply the linear differentiation operator. The derivative of t to the n is n times t to the n minus 1. The maximum value of this new output occurs at t equals 1. Plugging that in shows that the peak height, the output norm, is now exactly n. To find the stretch factor, we divide that output of n by our input of 1. This is the trap. As we choose higher powers of n, the stretch factor increases without limit. This proves that a perfectly linear operator can completely tear apart an infinite dimensional space. Theorem 2.7-9 resolves this tension. It states that for linear operators, boundedness and continuity are exactly the same thing. The bounding constant acts as a Lipschitz condition. If the inputs are infinitesimally close, the limit on the stretch factor mathematically bars the outputs from flying apart. To show continuous implies bounded, we look at the origin. If an operator is continuous at 0, we can take that local stability and scale it outward to any vector at the edges of the space. This topological cloning from the origin to the rest of the space only works because the operator is linear. Theorem 2.7-9 allows us to verify the topological stability of a linear system by simply confirming its geometric operator norm. Bounded linear operators restrict geometric stretching. The operator norm quantifies it, and Theorem 2.7-9 links it to topological continuity. This distinction between the bounded and the unbounded defines the limits of classical intuition. Understanding exactly where boundedness fails, as we saw with the differentiation operator, is required to map the quantum world. Pioneers like John von Neumann utilized this exact framework to systematize quantum mechanics. By isolating these unbounded operators, he could rigorously define physical observables like momentum and position within a consistent mathematical space. If this look into functional analysis geometry clarified the material for you, like and subscribe. Leave a comment with the specific chapter, proof, or theorem you want decoded next.